Hello, it's Dave Giles here for the next lesson of Cambridge International Education IGCSE Physics Units P1 Forces, Motion and Energy. And today we're looking at turning forces or moments. So I want you to describe turning forces and use the formula for moments. And you apply the law of moments to equilibrium scenarios and calculations. So starting with the first learning objective. Bob can't change the tyre at the side of the road. Other than going to the gym for a little while, what might help him here? So he can't make himself any stronger. How else could he loosen the nuts on the tyre? So the easiest way, apart from, like I say, working out a bit more, is to use a longer wheel brace, it's called here. Or in this case, it's actually an extendable one. So you make it longer so it's easier to loosen it off to change the tyre. And that is something that is quite common to use in cars because it saves space, you extend it, and then when you extend it, it's a lot easier to loosen these off. So what is a moment? A moment is a turning force. The size of the turning effect caused by a force depends on two factors. The bigger the force, the larger the turning effect, and the larger the perpendicular distance from the pivot, so how far away it is from the pivot, to the point where the force applied, the larger the turning effect. You can see here on a seesaw. So what happens to the seesaw when a force applied on the left-hand side? Well, when a force applied on the left-hand side, this side will move down, this side will move up, or we can say it experiences a moment. Rather than use the term up and down, it's going this way around, so that's an anti-clockwise moment. So to work out the size of a moment, we've already said it depends on the distance from the pivot and the size of the force. So from that, we can come up with this equation. Moment is force times perpendicular distance from the pivot. And because force is measured in newtons, perpendicular distance from pivot is measured in meters, moment is Newton meters. Be careful not to write newtons per meter, because that is incorrect. It's newtons times meters, so it's Newton meters. And this here's a little diagram here explaining it, and this shows it's the perpendicular distance, so it's this direction here from the pivot. So it wouldn't be the length of the spanner here, it'll be this distance here when we're calculating the distance for the work at the moment. Okay, here are 5 quick questions for you to have a go. I pause it, I'll let you have a go, and then I'll put the answer on in a few seconds. The answer on the board. Okay, so the answers are there. Hopefully they're all okay, fairly straightforward. They're just quick questions. And that is the first learning objective completed. Describe turning force and use the formula for moments, although we will still use that within the second learning objective, which is apply the law of moments to equilibrium scenarios and calculations. So we've got clockwise and anti-clockwise moments, like we said before. And these two here look like they're sat the same distance away from the center or the pivot. So Tim produced an anti-clockwise direction, or rather an anti-clockwise moment. Mark produced a clockwise moment. They both sit the same distance from the center. The clockwise moment is larger than the anti-clockwise moment, so the seesaw will have an overall move in an overall clockwise direction. Now, to make them balanced, they both need to have the same size moment. This is where we get the principle of moments. It states if an object is bounced about a pivot, the sum of the anti-clockwise moments equals the sum of the clockwise moments. And we'll have a look at a quick example here. So I've got 2 weights. One's 10 newtons, one's 20 newtons. So the moment on this side it's 2 meters away, so it's 2 times 10, which is 20 Newton meters. On this side, it's 1 meter times 20 newtons, which is again 20 Newton meters. So they are balanced. So there will not be a resultant turning force. It's worth mentioning it would be an equilibrium as well, because the pivot here, this point, will provide a upward force. So the total upward force will be equal to 10 and 20, which is 30. Not a moment, just an upward force, so it is in equilibrium. Okay? A simpler way to look at how far away you put them is, okay, I've got one 20 Newton weight, one 10 Newton weight. You're going to put the 10 Newton weight twice as far from the pivot on the other side as the 20 Newton weight. So here is, you might not be able to see it very well, I've got two masses. And you can see there, they are both 200 grams. Might not be able to see it too well. One's 5 centimeters from the pivot. One is 30 centimeters from the pivot. So we can work out the moment by doing force times distance. So it's 2 for the first one. Now, I've got 2 by just multiplying 200 by 10. We should use 9.8, but just to keep the maths a little bit simpler. 2 times, so it's a 2, we'll say they're 2 Newton weights. 2 times 0.05, 5 centimeters is 0.05 meters, which is 0.1 Newton meters clockwise. We've also got this weight here, which is another 2 newtons. And it's 30 centimeters away, which is 0.3 meters. So it's 0.6 Newton meters clockwise. So the total moment, or so the total clockwise moment is 0.1 plus 0.6, which is 0.7 Newton meters clockwise. Where should I put another 2 Newton weight on the other side to balance it out? Well, if I put it at 35 centimeters to the left, then moment 3, or the moment, the anti-clockwise moment, will be 2 newtons times 0.35 meters, which is 0.7 Newton meters anti-clockwise. Alternatively, so there, I just kind of said it's going to be 35 and we just checked it, but I'll show you now how to actually work it out properly. The very, very similar one. Calculate a total moment on the right, and then where would I put a 2 Newton weight on the other side to balance it? So you might not be able to see it because of the resolution, but that's one of the 2 Newton weights is 10 centimeters away from the pivot. The other is 20 centimeters away from the pivot. So same as before, moment 1 is 2 times 0.1, because that's 10 centimeters, 0.1 meters. So 0.2 Newton meters clockwise. Moment 2 is 2 times 20 centimeters, or 0.2 meters, which is 0.4 Newton meters clockwise. Total moment, add them together, you get 0.6 Newton meters clockwise. So which point would I put the 2 Newton weight on the other side to balance it? So remember, sum of the clockwise moments equals the sum of the anti-clockwise moments. So the sum of the clockwise moments was 0.6, and that equals F3 times D3 force times distance 3. Now, the force, we're using a 2 Newton weight, so we can substitute that in for the force for 2, so 2D3. So D3 is 0.6 over 2, which is 0.3 meters, or 30 centimeters, to the left on the other side. So now, we'll have a look at some multiple choice questions. We'll start with some basic ones and move on to IGCSE paper 2 ones. So select the correct reason that explains whether or not this statement is correct. Forces can only turn an object clockwise about a pivot. So I'm going to say, start from the bottom. Yes, force can only turn an object clockwise. Well, that's not true, because it can also turn them anti-clockwise. No, force can only turn an object anti-clockwise. That's also not true, because it can turn them clockwise or anti-clockwise. It's impossible to say. Well, that is not true, because we can say it's false. No, forces can turn an object clockwise or anti-clockwise about the pivot. The answer is A. Question 2. The diagram shows a balanced seesaw of negligible mass. Which of the statements describes what will happen if an extra mass is added on top of the one already on the left-hand side? So we'll start from the top. Force R will decrease and the seesaw will begin to turn anti-clockwise. It will start to turn anti-clockwise. However, force R will actually have to increase to balance out the downward weight force. This goes back to Newton's laws here. Force R will decrease. Again, we know straight away that's not true. Force R will increase. Correct. And the seesaw will begin to turn clockwise. No, it'll turn anti-clockwise. So D, force R will increase and the seesaw will begin to turn anti-clockwise. Is correct. Question 3. Now, this is a past paper IGCSE paper 2 question. 45 Newton load is suspended at the 40 centimeter mark. So you see this is 0, this is 100 centimeters. A 90 Newton load is suspended so that the ruler is in equilibrium. Where is the 90 Newton load suspended? So here is at the 40 centimeter mark, which is 10 centimeters from the pivot. So 90 newtons, it needs to be half that distance on the other side. So it needs to be 5 centimeters from the pivot. So it needs to be 5 centimeters on this side. So it will be 50 to the pivot plus 5 is at the 55 centimeter mark. And last question. The diagram shows uniform beam pivot at its center. A student applies 2 forces, F1 and F2 as shown. Which row is correct? So the first one, we'll start from the top. The clockwise moment. So the clockwise will be going this way. F2, D2. No, because it's from the pivot, so it's not that. Clockwise moment F2, D2. We can rule that one out as well. Again, this one here is F2, D4. Sorry, the watermark has slightly covered that. Should adjust it. F2, D4. Let's have a look. F2, D4 is correct. So anti-clockwise moment, F1, D1. No, that's not from the pivot. So D is F2, D4, which I've already said is correct for the clockwise moment. Anti-clockwise will be F1 times D3. So the answer is therefore D. Okay, that's it for today. I'll be uploading the next lesson soon. So now you should be able to describe turning forces and use the formula for moments and apply the law of moments to equilibrium scenarios and calculations. Thank you very much, everyone, and I'll see you in the next video. Bye-bye.